Okay. Now you know how to find the state space model, which is nothing but state equation and output equation from the differential equation. Okay. Now you have a shortcut method, you can utilize that, okay, directly. Okay. So now we'll solve one problem based on the shortcut method such that you can easily understand. Now this is the differential equation of order 3. Now this is the differential equation of order 3. Now see here, order is 3. When order is 3, there are 3 state variables, okay? x1, x2, x3, okay? Now see here, now when order is 3, there are 3 state variables. Now you write directly, what is A matrix order? A matrix order is 3 by 3. A matrix order is 3 by 3. What is the last row of A matrix? The last row of A matrix is moving from right hand side to left hand side. Take the coefficients with opposite sign. Plus 2 means minus 2. Minus 7 means plus 7. Plus 6 means minus 6. Now 0, 1, 0, 0, 0. See here, this first row, first element is 0, second element is 1, remaining all 0. But when you write the second row, shift the bit position 1 to the right side. So here is the bit position 1, but that bit position is shifted to right side. Therefore, it will come to here and this is 0. Now this is the way you can draw the A matrix. Okay. Next, what is B matrix order? Tell me first. Now this is 3 by 3. Then definitely this is 3 by 1. Now 3 by 1. The last element of B matrix is a coefficient of U. What is the coefficient of U? 10. Remaining all are zeros. Next, what is the C matrix? C matrix order is 1 by 3. Therefore, C matrix order is 1 by 3. And C matrix is a fixed matrix. First element is 1. Remaining all elements are zeros. Okay. Now this is A, B, C matrices and order. Now this particular representation is called as, this way of representation is called as controllable canonical form. Controllable canonical form. This is the controllable canonical form, CCF, controllable canonical form. Okay. Now this is called as a controllable canonical form. This is called as controllable canonical form. So he is asking, represent the state space model in controllable canonical form. Then this is the procedure you just, a normal procedure is called as controllable canonical form. But sometimes the questions are asking like this, represent the state space model in observable canonical form. What is asking? Represent the state space model in observable represent the state space model in observable canonical form. Represent the state space model in observable canonical form means OCF form. So he is asking the questions like this. Represent the state space model in observable canonical form. So when he is asking the state space model in observable canonical form, so in observable canonical form, A matrix order is same, 3 by 3. B matrix is also same, 3 by 1. C matrix is also same, 1 by 3. Matrix orders does not affected in observable canonical form, only the elements are affected. Okay. So the A matrix in observable canonical form is a transpose of the A matrix in the controllable canonical form, which means that 0, transpose of this 0, 1, 0, 0, 0, 1, minus 2, plus 7, minus 6. This is the A matrix in observable canonical form, which is the transpose of A matrix in the controllable canonical form. Next, in B matrix, now see here, this is B0, B1, B2. This is starting, this is ending. Okay, so that starting ending position should be reversed here. Therefore, now you start B0 here. This is B0, B1, B2. Means now the top to bottom elements will be coming here, bottom to top. Now, which means that here 0, 0, 10. In the same manner, C matrix also. This is C0, C1, C2. Right, left to right will be converted to right to left. Therefore, now this is nothing but 0, 0, 1, and now here it is C0, C1, C2. Okay, so here top to bottom, here bottom to top, here left to right, now here right to left. Okay, right to left will be combined. This is the controllable canonical form and this is the observable canonical form, and in the shortcut method you can get the answer. Even if you go for the classical method, general method, then we'll get the same answer. Okay, so this is controllable canonical form, this is observable canonical form. If the question represent the state space model in observable canonical form, as it is you find in the controllable canonical form, and a transpose and shifting from right to left and left to top to bottom will be get the observable canonical form matrices. Okay, no doubt. Okay, now we just solve one question and we will close this state space model from the differential equation and we'll go for another. Okay, now you just see here. Now this is the differential equation now, which is given as phi. This is phi dots. Now this is 4 dots. Now see here. Now 1, 2, 3, 4, 5. Therefore, A matrix order is 5 by 5. Now first you should write the last row first. Okay. Now the last row I am saying, moving from right hand side to left hand side, take the quotients with opposite sign. Minus 9. Now plus 6 means minus 6. Most of the students are writing like minus 6, which is a wrong approach, wrong. Now see here, this is y. After y, we required y dash. What is y dash? There is no y dash here. If there is no y dash, what should you write? 0. Y double dash plus 6 means minus 6. Y triple dash minus 7 means plus 7. 5 by 5 matrix. Okay. 5 columns, 1, 2, 3, 4, right? 1, 2, 3, 4. Now this is minus. So this is the A matrix last row, A matrix last row. What is the first row? I am already saying that the first row, first element, second element is fixed. 0, 1, 0, 0, 0. Now next, 0. Shift the bit 1, binary 1 position to the right side. Shift the 1 position to the right side. Shift the 1 position to the right side. That's it. Now this is 5 by 5 matrix. This is 5 by 5 matrix. Now B matrix 1 by 5. Oh, sorry. 5 by 1. And a B matrix last row, you know that quotient of U is 3, remaining all are zeros. C matrix order is 1 by 5, 1 row, 5 quotient. This is fixed, the first element is 1, remaining all are zeros. This is A matrix, this is B matrix, this is C matrix. This is the controllable canonical form, CCF form. And you go to home and write observable canonical form. Transpose of A matrix, and top to bottom elements will be shifted from bottom to top. Right to left elements will be shifted to left to right. Okay. Now this is the differential equation. I hope you must have some confidence how to find the state equation and output equation. Now how to get the state space model from the differential equation concept, right? Then we'll go to the next concept. First you take a copy of this. Okay, now we'll go for the next concept, how to get the state space model, from the transfer function, okay, how to get the state space model from transfer function means finding state equation and finding output equation. Okay, now let us check with one problem, you can easily understand. Now this is the transfer function y of s by u of s, which is equal to 2s plus 3 by s square plus 8s plus 9. This is the transfer function which is given to you. State space model transfer function, Laplace transformation of output by Laplace transformation of input is this. Okay, 2s plus 3 by s square plus 8s plus 9. Right. Now see here, this is the state space model transfer function. So now anyway, our normal procedure will be same. Order is 2. So two state variables x1, x2. Order is 2. Therefore, two state variables x1 and x2. Therefore, now you tell me what is A matrix order? A matrix order is same 2 by 2. Therefore, A matrix last row is from the denominator polynomial. Take the quotients with opposite sign will be the last row. Plus 9 means minus 8. Minus 9 plus 8 means minus 8. Now first element, first row is always a fixed row. First element is 0, second element is 1. You know that. A matrix, there is no confusion. Almost the same procedure as the differential equation. What we are doing in the differential equation, the same will be continue for A matrix only if the transfer function is given. Next, B matrix. First I will write B. B matrix is calculated from numerator polynomial. A matrix is calculated from denominator polynomial. Now, B matrix is calculated from so what is the numerator polynomial? This is the numerator polynomial. Now, common factor of numerator polynomial. What is the common factor? Let us take, for example, 2s plus 4. If it is a 2s plus 4, 2 is a common factor, s plus 2. This is the common factor. Let us take, for example. But what is in our problem? Our problem is, in our case, is 2s plus 3. Therefore, what is the common factor? No common factor. Therefore, we can write 1 as a common factor, 2s plus 3. Therefore, this is 1. So, while writing the B matrix, you can from the B matrix is calculated from the numerator polynomial. So, in the numerator polynomial, you should take the common factor of numerator polynomial. For example, this is the common factor, but in our problem, this is the common factor. Then what is the B matrix? First you tell me. The B matrix order is fixed, already fixed it is. Now this is 2 by 1 because this is 2 by 2. Therefore, now this is the last element. The last element is a common factor in the numerator polynomial. The common factor in the numerator polynomial is the last element of B matrix, which is nothing but 1. Remaining all are zeros. Remaining all means only 1. Okay. So B matrix last element is 1. The 1 is nothing but common factor of numerator polynomial. Understand or not? Common factor of numerator polynomial. If this is the case, so you should write 2 because the common factor is 2. But in our example 2s plus 3, so the common factor is 1 will be the last element. Next, C matrix. C matrix is calculated from numerator polynomial again. C matrix is calculated from numerator polynomial. And s power 0 quotient plus a1 s power 1 plus a2 s power 2 plus a3 s power 3 and so on. This is numerator polynomial. Now these are the quotients of a numerator polynomial: s power 0 quotient, s power 1 quotient, s power 2 quotient, s power 3 quotients and so on. Okay. So the C matrix is you know that. Now what is the C matrix? Now this is 2 by 2, this is 2 by 2, this is 1 by 2. But the coefficients, C matrix is calculated from numerator polynomial, coefficients of s power 0, s power 1 and so on. So s power 0 quotient and next s power 1 quotient. Because now there is s power 0 quotient, the s power 0 quotient is 3 and s power 1 quotient is 2, because this is nothing but 3 into s power 0 plus 2 into s power 1. Therefore, this is s power 0 quotient is 3. Now s power 1 quotient is 2. This is the way you can write the A, B, C matrices state space model in controllable canonical form if the transfer function is given. Okay, note down. Okay, now you just try yourself. Now this is the transfer function which is equal to 5s plus 10 by s cube plus 9s square minus 8s plus 3. Okay, so now you tell me order is first order is 3, therefore x1, x2, x3, 3 state variables. So calculated from denominator polynomial, A matrix order is 3 by 3. So if A matrix order is 3 by 3, what is the last row? Move from right hand side to left hand side. So take the quotients with opposite sign. Plus 3 will becomes minus 3, minus 8 becomes plus 8, plus 9 will becomes minus 9. And first row is fixed row. First element and second element is fixed 0, 1, 0. Remaining is just shifted by 1 bit position to the right. Now 1 bit position to the right. So this is the A matrix. This is A matrix. This is the A matrix from the denominator polynomial. Okay. Now B matrix is calculated from the numerator polynomial. What I am saying, B matrix is calculated from the numerator polynomial, common factor of the numerator polynomial. Now what is in our example? Now in our example, this is 5s plus 10. So is there any common factor? Yes. If you take 5 as a common, now this is, if you take 5 as a common, s plus 2. So 5s plus 5 into 2, 10. So the last element is the common factor in the numerator polynomial. The common factor in the numerator polynomial is 5. Remaining all are zeros. Remaining all are zeros. So but first order is 3 by 1. So remaining all are zeros. Okay. Next, C matrix is calculated from the numerator polynomial. Now C matrix order is 1 by 3. So s power 0, s power 1 and s power 2 is also coming. So what is s power 0 quotient? S power 0 quotient is 10. S power 1 quotient is 5. S power 2 quotient is 0. Which means that now this is 10 s power 0 plus 5 s power 1 plus 0 s square. This is from the numerator polynomial. Okay. Now this is C matrix. This is B matrix. This is A matrix. Okay. Easy. Not wrong. Now one more transfer function here is now this is the transfer function y of s by u of s, which is equal to 1 by s plus 1 into s plus 2 into s plus 3. Okay. Now this is y of s by u of s, which is equal to 1 by s plus 1 into s plus 2 into s plus 3. So now first we will do the partial fractions for this. So y of s by u of s, which is equal to a by s plus 1 plus b by s plus 2 plus c by s plus 3. So if you do that, now y of s by u of s by u of s, which is equal to, now this is a is 1 by 2 by s plus 1, b is minus 1 by s plus 2 plus c is 1 by 2 by s plus 3. So can I write like this? Now this is nothing but, can I write like this? Now y, which is equal to 1 by 2 by s plus 1 into u plus minus 1 by s plus 2 into u plus 1 by 2 by s plus 3 into u. Okay. Now see here, partial fractions. Now this I just u multiplied with these three terms. Okay. So now let us take this is y, which is equal to, this total is x1 plus this total is x2 plus this total is x3. Okay. So now let us check here. Now what is x1, what is x2, what is x3? Now x1, which is equal to 1 by 2 by s plus 1 into u. So this is nothing but s x1 plus x1, which is equal to 1 by 2 into u. So this we can write s x1 is nothing but x1 dash x1 dot, which is equal to, then x1 is come to this side, minus x1 plus 1 by 2 into u. Now similarly, what is x2? x2, which is equal to minus 1 by s plus 2 into u. So this is also you can cross multiply s x2 plus 2x2, which is equal to minus 1 into u. Therefore x2 dot, which is equal to minus 2x2 minus 1 into u. Okay. Now x3, what is x3? Finally x3 is 1 by 2 x plus 3 into u. Then if you cross multiply s x3 plus 3x3, which is equal to 1 by 2 into u. So this is x3 dot, which is equal to minus 3x3 plus 1 by 2 into u. Okay. So same general our normal procedure what we are doing, with the same procedure we can do this. Okay. So now you know x1 dash equal to something, x2 dash equal to something, x3 dash equal to something. Okay. Now I will try to write the state space model is nothing but state equation. Now see here, x1 dot, x2 dot, x3 dot. Now this is 3 by 1, which is equal to, now you know that this is 3 by 3 into x1, x2, x3 plus this is also 3 by 1 into u, you know that this is only 1. Okay. So this is 3 by 3, this is 3 by 1, this is 3 by 1, this is 1 by 1. So see here, in x1 dash x1 is there minus 1, in x1 dash x2 is not there, x2 is not there, x3 is not there, u is there 1 by 2. In x2 dash x1 is not there 0, x2 is there minus 2, x3 is not there 0, u is there minus 1. In x3 dash x1 x2 is not there, x3 is there minus 3, u is also there 1 by 2. Okay. Now this is y. Y is nothing but 1 by 1, which is equal to, now you know that this is 1 by 1, but this is already fixed. This is x1, x2, x3. Now this is 3 by 1. Now this is 1 by 3. Now see here, what is y here? Y equal to x1 plus x2 plus x3. So y is x1, y in terms of x2, y in terms of x3. Therefore, 1, 1, 1, x1, x2, x3. This is A matrix, this is B matrix, this is C matrix. Order is 3, therefore A matrix order is 3 by 3. Clear or not? Same general first procedure. What is the first procedure I am writing? Right, from the differential equation. So this is cross multiplication, means again I convert into differential equation. When the differential equation is available, a general procedure. Okay, note down this. Okay, now you understand this procedure. This is the general procedure. Okay, now where we start this topic, now the same procedure. Okay, now you just listen here. Now forget about all these things. See the transfer function. This is the transfer function. Now what is the order of the transfer function? The order of the transfer function is 3 by 3. This is the transfer function. Now what is the highest power in the denominator polynomial is 3. Order is 3. So if order is 3, you know that A matrix order is 3 by 3. Now see here. A matrix order is 3 by 3. Now see here. Now whatever the closed loop poles are available, that poles you should write in a diagonal form. This is -1, -2, -3. Remaining all are zeros. So see here. Now A matrix order is 3 by 3. Now if the denominator polynomial roots are available, now which is nothing but, let us assume closed loop poles. That closed loop poles you should write in the diagonal form and remaining all are zeros. What is the answer you are getting? -1, -2, -3. Same general procedure and the shortcut procedure will use the same or not? Yes. Next, B matrix. Now this is 3 by 1. See here. Now B matrix coefficient is nothing but partial fraction coefficients. What are the partial fraction coefficients? See here. What are the partial fractions? Partial fraction coefficients. A is 1 by 2, B is -1, C is 1 by 2. Now that partial fraction coefficients will be the B matrix elements, which means that 1 by 2, -1, 1 by 2. In general procedure, what you are getting? 1 by 2, -1, 1 by 2. This is the general or lengthy procedure, and this is the shortcut method. Will give the same answer or not? Yes, will give the same answer. Am I right or not? Next, now C matrix. C matrix is a fixed matrix. C matrix is a fixed matrix. All elements are 1, 1. C matrix is fixed. All are ones. All elements are ones only. Sir, how we can know that? Sir, all elements are 1. How I can identify that? Because you know that this is totally x1. This is totally x2. This is totally x3. Y equal to x1 plus x2 plus x3. Therefore, y equal to x1 plus x2 plus x3. 1, 1, 1 is the C matrix. Okay. Now, this is the 1, 1, 1 C matrix and this is 1, 1, 1 C matrix. Will be matching or not? Yes. Therefore, now this is the shortcut method. There is no need to do this lengthy procedure. Okay. Don't follow this lengthy procedure. For understanding purpose, I am writing to you. Okay. Now this is the shortcut method. Then you follow this shortcut method and you can get the answer directly. Now if you observe here, now all the closed loop poles, now these are the closed loop poles which are available in the diagonal. Therefore, this type of representation is called as diagonalization form. Diagonalization form of state space model. He is asking the question. So like this transfer function is given. Like this, a differential equation is given, and he is asking, represent the state space model in diagonal form. Represent the state space model in diagonalization form. So you can use this shortcut method and you can get the answers. Okay, note down this. This is the shortcut procedure to find the state space model matrices now from the differential equation or from the transfer function. Okay, note down. And one note here. One note here is, so sometimes in the options, now this will be same, okay, sometimes this B is not here, whatever you are getting B, that is not there in B, so then you have some confusion. Sir, I actually partial fractions quotient, but there is no options is having a partial fraction quotient, but that is not there in B, but that is there in C. And what is C? 1 1 1, but that may be in B. So which is correct? Yes, the note is in diagonal form. In diagonal form, B and C are interchangeable. Okay. Now maybe whatever you are getting B, it may be in C. Whatever you are getting C, it may be in B. Okay. So B and C matrices are interchangeable in diagonal form. Okay, no.